Welcome to Digital Systems. This is the first in a series of short videos that I will be attaching to my lecture notes. And this first video is about implementation of digital systems. Now it's really interesting that digital systems existed before we discovered electronics. If you imagine that you're in a castle and you see enemies approaching and you climb up the tower and you are somehow able to send flashes of light to a neighbouring castle on a hill far away, then you're able to send them messages such as help. If we think about this in greater detail, I know Morse code probably wasn't invented back then, but if we think of Morse code, the letter S is given by ... the letter O is given by ... and SOS, meaning Save Our Souls, is the international symbol for help. So if we need to send out the message help, and it's too far for voice to be used, voice is an analog means of communication because there are an infinite number of different sounds you can make, roughly speaking. If we want to send out SOS in the digital way, then we can get a light reflected from the sun or whatever and go ... And the person receiving that can take that digital message, which only consists of off when there's no light or on when there is light, so it's digital, and they see 3 short flashes, flash, 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 and they know that means the letter S. And there's a slight pause, so they know that it's the end of the first letter. And then they see a dash, 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 and a slight pause, and they know it's the end of the second letter. Then they see a ... and they know that that's the third letter S. They get SOS, and they've understood the message. Now in modern systems, the same thing happens. We take an actual message that we want to send, maybe even my voice. We somehow encode it in the digital domain. We now have more sophisticated ways of doing this than using Morse code. But whenever you make a telephone call, your voice gets translated into the digital domain and it gets transmitted digitally across our digital network. In fact, the backbone of our networks are usually fibre optic cables, and they use the same principles that we talked about with the castle. A fibre optic cable carries digital signals encoded by, at one end you've got a light, a laser, that's either on or off, and it just gets sent down that cable to the other end, and the receiver at the other end just detects flashes of light and somehow converts that back into the original message. So in modern days, the way we build digital systems electronically is that we just take a circuit, maybe you can't see it, it's a bit small, but provided each wire just carries 2 voltage levels, either 0 volts or, for example, 5 volts, then we can talk about this being a digital circuit because the information is represented on each wire using only 2 states, no voltage or full voltage, 0 or 1. It turns out, and we'll learn about this later in the course, that you can design digital systems using only things known as transistors, which are, roughly speaking, 3-legged devices, and there are different types of transistors. You can use any type to make a logic gate, but we'll see later why field effect transistors are particularly nice for making logic gates. We just need to use these transistors and we can implement any digital circuit we want. Remember that a computer is an example of a digital system, and it processes vast amounts of information very quickly. It's fair to say that any information that humans want processed can be done in the digital domain. There might be some small exceptions where it's easier to do in another domain, but in the digital domain we can certainly process information quickly and efficiently. So how do we go from having little transistors here that can somehow process signals and having these LEDs that allow us to display digital signals How can we build more complicated things? Well, in the olden days that was a bit of a challenge. We'd physically have to solder circuits together or build them using boards like this if they existed. And because a single transistor is a little bit limited in what it can do, people also made these silicon chips. Now these are about 40 years old. By the process of entropy, all good things that my father has end up in my house. So I've inherited these 40-year-old logic gates and different circuits here. So to make it a little bit easier for engineers to build things, companies would take tens or hundreds of transistors and put them into these silicon chips. And then because there's 10 or 100 or so of these little transistors in this chip is a bit more powerful than this single transistor, a bit more convenient to use. Now this particular chip, it says it's a BCD to 7 segment decoder driver. And what this means, BCD is a binary coded decimal, and we'll actually be using this in the labs a bit later. What it means is that I can represent numbers in a convenient way in the digital domain. So if I want to represent the number 0, then I'm going to use, and I'll explain why I'm going to use 4 bits in a second. To represent the number 0, I need to send over 4 wires 0, 0, 0, 0. Or in other words, the voltage is 0 on these 4 wires. If I want to send the number 1, well, 1 in binary using 4 bits is 0, 0, 0, 1. And if I want to send the number 10, well, that's 1, 0, 1, 0 in binary. So using just 4 wires, I can send a number between 0 to 9. In fact, I can send larger numbers, I mentioned 10, and I can send up to the number 15, which in hexadecimal is the letter F. So, binary coded decimal is basically saying if I want to represent a number between 0 to 9 using 4 wires, then I do it using binary, and I accept the fact that I'm wasting the numbers 10 to 15. BCD to 7 segment decoder. What's a 7 segment doohickey? Well, over here, and it's wrapped up in its box, but here's another chip, and we'll be using these things just in a more convenient form in this course. This little doohickey actually contains 7 LEDs, and they are arranged in horizontal and vertical orientations, and you would have seen this before. You can use this to display a single digit and use, say, 4 of these to make a clock. So if I want to display the number 1, I need the LEDs on the right-hand side to be lit and all the other ones to be off. There are little pins here, and I have to provide the correct voltage to each of these pins. I have to provide, depending on whether it's active high or active low, I have to provide either 5 volts or 0 volts to these pins to get the lights to do what I want them to do. And if I'm making a clock, I need to be able to display the digits 0 to 9, and it's a bit complicated for me to work out all the different combinations I need to get those different digits to display. So I can use a BCD to 7 segment display. I wire these up in a clever way. Basically, some of these pins, and how do I know which pins? Well, that's why you also buy books in the olden days that would contain the data sheets telling you what all the different pins used to do. And not that you can see, but there's actually a description on the back of this package too that tells you how to wire it up. Some of these pins connect directly to the 7 segment display. They are the output of this chip here. And there should be 4 input pins. Because it's binary coded decimal, I know that there are going to be 4 input pins here. And so if I put on these 4 input pins 0, 0, 0, 1, meaning I attach the first 3 pins to ground and the 4th pin to 5 volts. If I put in 0, 0, 0, 1 on the input and I apply power to this chip, then the output pins that are connected to the 7-segment display are going to be such that the number 1 appears on this device here. So somehow in this little chip here, using nothing more than lots of little transistors, it is somehow able to take the input signal, which to humans represents a number between 0 to 9, but to a piece of silicon, it's just voltage levels. It takes these voltage levels, a digital signal, and applies the correct voltages on the output, again digital signals, to turn on and off the different segments of this display so that we see the correct number. If we put in 0011, which for humans represents the number 3, then the output pins here are going to be such that the number 3 displays on our 7-segment display here. That's a simple example, well, not that simple, but it's a relatively simple example of a digital circuit. Over here we have a quad 2-input multiplexer. Quad means that there are 4 of these multiplexers on this one chip. 2-input multiplexer is something that we're going to learn about a bit later in this course. This chip over here is a serial in, parallel out shift register. And again, we're going to learn about shift registers in this course. This little device here is a synchronous up-down counter with preset inputs. In other words, if I want to make a clock, I need to be able to count. I need the input to my BCD decoder, I need the input to go from 0, 1, 2, 3, 4 to drive the digits on my clock. And so I need a counter to do that. And that's exactly what this little doohickey is supposed to be doing. In fact, this guy can count either up or down. And in our course, we're going to see how to build counters. In the olden days, building counters was very difficult. It was better to just buy one of these things here. But we'll see that in the modern era, it's very easy to build our own counters. Lastly, over here, I've got a dual JK master-slave flip-flop. Now, dual, remember, means that there are 2 such devices on this. So in this chip here, there's actually 2 flip-flops. Flip-flops are one of 2 essential things for digital circuits. All digital circuits are made out of logic gates and flip-flops. Now, inside a logic gate are just transistors, and inside flip-flops are just transistors. So in some sense, the only thing we need are transistors. But in terms of the convenient building blocks, we're going to be talking about logic gates and flip-flops in this course. Flip-flops have got memory, and we're going to learn about them after we've learned about logic gates. But then that's it. Once we know about logic gates, once we know about flip-flops, then we know the foundations of digital systems, so to speak. In the olden days, if we wanted to build a digital circuit, first we'd have to get pen and paper, try to design it. If you've ever done any electronics, you know that you can draw pictures of transistors and resistors and capacitors and LEDs. Well, you can also draw pictures of logic gates, and you can design your electronic circuit on paper. Then you find some way of implementing it by soldering it up or whatnot. In case you haven't seen a chip up close, this is a silicon chip, and if you need to use it, then you carefully take it out. It's got little pins under there, and you can put this into a PCB and solder it up or whatever. Let me put this back before too much harm comes from it. So in the olden days, it was very painful to build digital systems. First, you designed it by hand. Then you had to design a printed circuit board or some other technique. Then you had to solder it up. And then of course it would never work. And so then you have to figure out why it doesn't work. Then you change your design. unsoldering and resoldering is very hard. You could either try to do that or start again, and the process was very long and very tedious. And it's really, really remarkable that we don't have to do any of that anymore, because we've got this fantastic thing here. And those of you that are able to come onto campus will have the luxury of being able to use these boards. If we quickly open it up, let's have a look what's inside. We will see that we have a USB cable. So this board is going to plug into a computer, and the computer we're going to run some software called Quartus, and we basically tell Quartus what we want our digital circuit to do, and Quartus figures out how it can do it using logic gates and flip-flops, because that's the only thing we have in digital electronics. And then, and this is the really cool thing, this great big chip here in the middle of this board is what's known as an FPGA, Field Programmable Gate Array. We'll be learning a lot more about the architecture of this FPGA later in the course, but right now all you need to do is imagine that inside this FPGA are lots of little men, and when the computer, via the USB cable that gets plugged in here somewhere, when the computer tells the little men what circuit to build, the little men go and build that circuit in that chip. And then when we finish programming it and actually use this FPGA that has been configured via the computer, via the little men in here doing the soldering, so to speak, we have a digital circuit in here that we've designed. We can then use it. We can press these push buttons here, flick these switches here. These switches are connected to pins of our FPGA. That's what this board does. Other pins of this board are connected to here are our 7-segment displays here, where we can display numbers. And so when I press a button, that changes a signal on a pin of the FPGA. If we've told our little men inside the FPGA to wire up some logic gates that take what's coming into that pin, do some processing using logic gates, and send the output to another pin that's connected to one element of the 7-segment display, then in response to pressing buttons and flicking switches, I can get things to display on the 7-segment display. And if I make a mistake, I just go back to this software called Quartus. I have access to software debuggers that make it much easier for me to figure out where the problem lies. I make a change to my code, I recompile, I send the configuration to this FPGA. That means the little men inside this FPGA erase the original circuit and build my new circuit for me using the logic gates, and then I can test it out on this board and see if it works. And this is a really big time saver, not just a little bit, tremendously so. It's also got important commercial applications. In the olden days, when you bought a device, an electronic device, that was it. You were stuck with what you had. But now we are so used to these firmware updates and software updates. What this means is that if you design a new digital product and you put inside it an FPGA, and then a year down the track you realize there's a slight problem with your product, there's a bug in there, you can actually just send out the firmware to customers, if you planned beforehand, on a way of uploading new firmware. Provided you had a way of uploading new firmware, you could send out new firmware to your clients. They can just press the buttons or follow the instruction manual, and under the cover what's happening is you load up new firmware into the FPGA, you reconfigure the FPGA, and you've changed your device, and you can fix bugs with it, you can give it new features, etc. So we've really entered a new era of digital design, and this course is all about how to build digital circuits using FPGAs. If you're only going to be making a few products, then you might want to just stick with an FPGA. That might be true up to a few thousand products. But if you're going to be producing millions of products, then FPGAs end up being a bit more costly in very large volumes. You can actually take the skills you've learned in this course, and in fact using the hardware description language called Verilog that we'll be learning too, you can use that as well. You can actually get custom chips made. They're going to be cheaper if you order them in the millions or so. So for us, we're going to use FPGAs, that's the most convenient way, and that's what many products use, unless you're talking about products where there are millions and millions sold, in which case they might not have an FPGA, they might have what's known as an ASIC, a dedicated chip that's been designed specifically to do a certain task.